You know, for almost a century, physics has been living this weird kind of double life, operating with two completely different rulebooks for the universe. But what if one of them is just wrong? Today, we're diving into a cosmic mystery. Is gravity hiding a secret that could literally change everything we think we know about reality itself? Okay, so let's get right into it. The central question, first asked by the legendary Richard Feynman way back in 1957, is actually pretty simple but incredibly profound. Is gravity a quantum force, or is it something else entirely? For over 60 years, this question has just been hanging there, one of the biggest unsolved problems in all of science. So to really get why this is such a massive puzzle, we've got to look at the two great pillars of modern physics. It seriously feels like the universe is running on two different operating systems that just refuse to talk to each other. On one side, you've got Einstein's theory of general relativity. This paints a picture of gravity as this smooth, continuous, totally predictable fabric of spacetime. Think of it like a perfectly calm, glassy lake. But then, on the other side, you have quantum mechanics, and this describes the world of tiny particles as being jumpy, based on probability, and let's be honest, just plain weird. It's not a calm lake, it's more like a bubbling, chaotic stew. And the two descriptions just don't mesh. And this is not some new problem we just thought up. Even the great Richard Feynman was wrestling with it decades ago. And while he leaned towards gravity being quantum, he kept an open mind. He even considered the bare possibility that maybe, just maybe, quantum mechanics itself was the theory that needed fixing. So how on earth can we possibly test this? Well, modern physicists have turned to one of the most bizarre, most counterintuitive features of the quantum world: entanglements. You've probably heard of entanglement before, right? It's that spooky action at a distance Einstein talked about. It's this bizarre quantum connection between two particles. What you do to one particle, even if it's on the other side of the galaxy, instantly has an effect on its partner. It's a link that just defies all our everyday, classical intuition. So here's the key piece of logic, the whole game plan. Classical forces, the ones we know and love, can only communicate locally. They can't create that spooky, faster-than-light connection. So the theory goes like this: if we can show that the gravitational pull between two objects can entangle them, well then, gravity itself must be playing by quantum rules. Case closed. But, and there's always a but in physics, isn't there? Actually pulling off this experiment is a monumental challenge. I mean, it requires putting large objects into a quantum superposition, which basically means making them exist in two places at once, kind of like a spinning coin that's both heads and tails until it lands. That's something scientists are still struggling to do on any kind of large scale. And this is where our source material gets really clever. Instead of trying to build this ridiculously complicated experiment, a new paper proposes a thought experiment that reveals a deep paradox if you assume gravity is classical. It's all about pushing the laws of physics right to their breaking point. Okay, so let's set the stage. As with so many of these physics thought experiments, we've got our two heroes, Alice and Bob. They're far apart from each other, and they each hold one particle from an entangled pair. So Alice decides to measure her particle first. Because of that spooky quantum link, the very instant she makes her measurement, she instantly knows the state of Bob's particle, no matter how far away he is. Now, Bob's got this really clever setup. He sends his particle through a device that acts like a fork in the road. If the particle's spin is up, it goes one way. If it's down, it goes the other. And here's the crucial part. A tiny little probe is sitting there, positioned to feel the gravitational pull from the particle's path. Okay, now here's where it gets really mind-bending, so stick with me. What if Alice makes a different kind of measurement, one that forces Bob's particle into a quantum superposition, where it is both up and down at the exact same time, taking both paths at once? What in the world does Bob's gravitational probe feel now? And this is the paradox laid bare. See, if gravity is classical, it can't be in some weird quantum state. The probe has to be pulled either up or down. But which one? Its choice would have to depend on what Alice measured, maybe light years away. If that probe reacts instantly, Bob could use it to get a message from Alice faster than the speed of light. And that is absolutely, positively forbidden by the laws of physics. It breaks everything. So how do we get out of this paradox? Well, the paper proposes a solution that is both beautiful and completely surprising. To save that cosmic speed limit, a classical gravity needs a kind of escape hatch. And the proposed solution is this idea called classical diffusion. Okay, imagine trying to hold a pen perfectly still. No matter how hard you try, there's always that tiny, unavoidable tremor, right? The theory suggests that a similar jiggle or wobble might be a fundamental part of reality itself, a tiny random noise just baked into the fabric of space and time. So here's the crucial point, the punchline. For any classical theory of gravity to be consistent with quantum mechanics, to not allow for that faster-than-light communication, it must have this randomness built right in. This noise isn't a bug, it's a fundamental, mandatory feature. So what does this noise actually do? It's fascinating. Its randomness essentially scrambles the quantum information, forcing a particle in a superposition to pick a side and choose a single path. This move prevents Bob from ever knowing what Alice measured, which in turn saves the cosmic speed limit. And here's the most important part. This tiny gravitational wobble has to affect everything, even big classical objects that aren't in some weird quantum state. And this single insight completely changes the game. It means we don't have to perform those mind-bogglingly complex quantum experiments. We can actually hunt for evidence of gravity's nature in a much simpler, purely classical way. A new hunt can begin. I mean, the difference is just striking. The old way required wrestling with these huge quantum states to test for entanglement, a massive technological hurdle. But the new way? It's much more direct. Just monitor a very sensitive classical object and look for a tiny, random wobble that shouldn't be there. We've gone from the impossibly complex to the potentially achievable. The proposed experiment is just elegant in its simplicity. First, you build an incredibly sensitive torsion pendulum. Then, you cool it down to just a fraction of a degree above absolute zero to kill all the thermal vibrations. You shield it from every other possible source of noise you can think of. Seismic activity, sound, you name it. And then, you watch. You just look for a tiny, random motion that has no other explanation. So this brings us to the final, thrilling part of the whole story. What happens if we actually run this experiment? The implications of either outcome, well, they're truly profound. Okay, so if we find this mysterious wobble, it would be staggering. It would suggest that gravity might actually be a classical force after all, and we would have discovered a new, fundamental source of randomness in the universe. But if we perform the experiment with enough precision and find nothing, no wobble at all, that would be an incredibly strong piece of evidence that gravity is quantum, just as most physicists have long suspected. So we're left with this absolutely fascinating question. An experiment that isn't looking for exotic new particles or hidden dimensions, but simply for a tiny, unexplained jiggle in a cold, quiet pendulum. And the answer, whichever way it goes, could fundamentally change our entire picture of reality. It's a powerful reminder that sometimes the biggest secrets of the universe are hiding in the very smallest of motions.